Good evening, everyone. My name is Kim McMahon. I'm a meteorologist with the National Weather Service in Burlington. If you can hear me, please type something in the chat box on the bottom of the menu. And actually, there is the word chat and a little plus sign next to it, in which case you can hit the plus sign and then should see the dialog box to type something in. Should I unmute? Okay, great. Thank you. Okay, so we will get started. Like I said, my name is Kim McMahon. I'm a meteorologist with the National Weather Service. I've been in the Burlington office for about 4 years, and then prior to that I was in the Albany, New York office for about 8 years. And this presentation is just a kind of a one-on-one on winter mixed precipitation. So please save any questions for the end. All phones will be muted, and at the end of the presentation we'll answer a few select questions. I won't be able to get to all of them, at least not in the time frame that we have, but I pick a few to answer for everyone to hear. This presentation is being recorded, so we will be posting this on our YouTube channel in the following weeks once I have a chance to go through and edit it. And we should take about 30 minutes. So what we're going to cover is some climatology for the North Country, both snow and freezing rain, different types of winter precipitation and how each of these form, and then how to measure some winter precipitation. Then we're going to end on a case study which occurred a little less than 2 years ago. It was December 21st, 22nd event of 2013. Some facts for you. Injuries that are related to snow and ice, 70% of them results from vehicle accidents, and 25% occur to people caught out in the storm, specifically a winter storm. And most of these injuries happen to males over the age of 40. So moving on to our climatology, this is a graph showing, or I should say a map, showing the average annual snowfall for the North Country, and you can see in the purple color the mountains, Adirondacks and the Green Mountains, really highlighting the terrain and therefore the higher snowfall amounts. And obviously in the valleys, such as the Champlain Valley, Connecticut Valley, and St. Lawrence Valley, less snow occurs there. And in Burlington, we get about 80 inches every year, or I should say an average of 80 inches a year. Now moving on to our freezing rain climatology, this graph shows the number of occurrences of freezing rain reported by ASOS, which is our Automated Surface Observation Systems, across the North Country each month during what we defined as the cold season, being October through April for the past 10 years. And you can see in October we start off pretty low with only a few occurrences. Sorry, my screen just went black. There we go. Okay, so you can see that in October we do have a few occurrences, and November increasing, but we peak in December when we really start to have colder air really take hold of the North Country, with the exception of this month so far. And then as we continue to just have cold air throughout the column of air above us, the number starts to drop as far as the frequency each month. In January and February, we have a slight secondary peak in March because we start to have that warm air as we approach spring. Then looking by location across the North Country, our winner for the most occurrences of freezing rain reports is Messina, New York. And as we go from left to right, Plattsburgh, New York is pretty much the lowest out of our automated surface observation systems. Then Saranac Lake and Burlington climb back up, with Montpelier and Springfield actually tying at about 639 reports, and this is just every time that observation system reports freezing rain. And in between Montpelier and Springfield, Vermont, Morrisville is more along the lines of Plattsburgh. So now as we go into the different types of winter precipitation, we'll be talking about snow, sleet, freezing rain, not so much rain because, as you can see from this graphic, you just have a deep layer of warm air all the way to the surface, so therefore any ice crystals or snow melts and continues as rain. What we need in order for any mixed precipitation to occur, first thing, we need moisture, obviously. Without moisture, you can't have any clouds, and therefore no clouds, you're not going to have any precipitation. We also need cold air and warm air for the mixed precipitation. Now, one of the key things about understanding how mixed precipitation forms is you have to think of the atmosphere as a column. You have the surface at the bottom, and then, of course, you have up further in the atmosphere. Just think of it as a column over an area. And the last thing you need is lift, something to provide the air or force the air to rise, be it a front, upper level low, and low being low pressure system, or the higher terrain that we are all familiar with in the North Country. For the purpose of this talk, we'll be focusing on the moisture and the cold and warm air for the mixed precipitation. We start with the clouds, where it all begins. You do need adequate moisture to form clouds and precipitation, and you do need that cold air combined with the moisture to form ice crystals and supercooled water droplets, which are just water that is still in liquid form below freezing temperature, 32 degrees Fahrenheit or 0 Celsius. And we'll discuss that supercooled water droplets a little later in this presentation. Then you do need warm air, and depending on the depth, intensity, as in how warm it is, and the location of where the warm air is located within the column, that will determine what precipitation type you'll get. And you can kind of see a little depiction of that, or a simple depiction of that, in the graphic on this slide. So we have rain on our left-hand side as cold ice crystals or snow fall into the warm air and melt, continue down to the ground as rain. Freezing rain, the same thing happens, except right above the surface or the ground, the temperature becomes colder again and below freezing, and therefore when the rain droplets land on something, they start to freeze onto the ground, cars, streets, sidewalks, anything that's cold. Then as we continue a little further to the right of that picture, sleet, just the layer of cold air at the surface, is even deeper. And snow, the warm air doesn't have a chance to even melt the snow, and therefore it remains freezing. So on this slide, starting with snow, it's very basic. You can see that on the little video, which I hope is working for everybody, the snowflake starts off in the cloud and starts to fall due to gravity, and the temperature remains cold enough where it can stay snow until it reaches the ground and hopefully accumulates on the ground for those snow lovers out there. Next to that little video, there is a depiction of what we call a sounding, and basically that red line is the temperature. And I know it's showing it in Celsius, but 0 degrees Celsius we know is freezing. So you can have cold air starting at the top, and then as the snowflake falls, you can actually have the snowflake go into some warm or above freezing air, as long as it's for a short period of time or a short depth, and it's not very warm, just about 1 degree Celsius. And then, of course, as you continue, you can see the temperature come back below freezing to the left of that 0 C line, and therefore it remains as snow and no melting occurs. Another way to think of this, you can see the graph on the left-hand side. And this is just using 32 degrees instead of the 0 degrees Celsius. We have the deep cold layer air that's actually shaded in blue, and the temperature line is that green dashed line. So therefore, you can see on this, the temperature never actually goes above freezing, and result in some of the pictures on the right, white snow covering pretty much everything. Moving on to sleet or ice pellets, and I do want to make that distinction. I grew up on Long Island, and unfortunately the misnomer there was that sleet was a mix of rain and snow. It is not. Sleet is actually when the snow falls into a warm layer, melts into liquid water, and then goes back down into a below freezing layer or cold air, and freezes, forming literally a little ice ball. So in this video you can see that the snowflake falls into this red warm air and melts, and then goes back into the blue and refreezes into that ice ball, and then bounces as it hits the ground. And as you look at the temperature graph just to the right of that, you can see that it corresponds with the temperature being below freezing, and then just going above freezing to the right of that 0 degrees Celsius line. Not very warm. It's only about 1 to 3 degrees Celsius, so partial melting occurs, and then as you get closer to the surface, as it continues to fall, the temperature falls back below freezing, and therefore it forms that little ice ball or ice pellet and bounces off the ground. You can see some photos on the left-hand side. It really is just little tiny ice balls, and one thing to keep in mind looking at the image on the bottom, freezing rain will form ice on surfaces and roadways, while sleet bounces off the surface. So as you look at the graph on the right-hand side, just a shallow warm layer of air is enough to have some melting, and then you go back into the cold and it starts to refreeze and literally bounce off the ground when it hits the ground. And for those interested, when the temperature, which is again that green dash line, goes above the freezing mark in this column of air, we call that a warm nose. So if you're ever reading our area forecast discussions and you hear that, you'll know what we're talking about. Now on to freezing rain. It's the same process as sleet, however, that layer of warm air, or that warm nose, is deeper and actually warmer. So you can see that as the snowflake falls through that deep layer of warm air, it melts completely, and then there's just a very, very shallow layer of cold air that's at freezing or below freezing, and it's not that shallow layer of cold air by the surface is not deep enough to allow that raindrop to refreeze. So it freezes on contact once it finally makes contact with something on the surface. And to reinforce that, looking at the temperature on the just to the right of that, the red line starts cold, reaches that 0 degrees Celsius mark. We have that warm nose, which is deeper and actually warmer than 3 degrees Celsius in this case, and then comes back down as you go closer to the ground, below freezing, but for a very shallow layer. So some examples of freezing rain. We have some berries covered in ice on the top right, and then beneath that, trees that are completely weighted down by all the ice. And as you guys probably know from the 2013 event that we'll go over later, those trees and branches wind up breaking and falling on power lines and unfortunately causing power outages. So just to reinforce the warm nose for freezing rain, excuse me, you can see that the sounding or temperature on the left-hand side goes well above freezing for a deep layer and just comes back for a shallow layer, and hence freezing rain. So to recap, rain is just when you have cold air, unless of course it's summer, you have cold air at the top, and there's enough warm air to cause all the snowflakes and ice crystals in that to melt and then continue falling as rain, and at the surface it's warm enough above freezing, so it just continues as rain. Freezing rain, that's when you start to get that very shallow layer of cold air near the surface, and you have a deep layer of warm air so above that, so all the snowflakes and ice crystals melt as they fall down, and unfortunately that shallow layer of cold air is not deep enough for the freezing rain to refreeze until it hits the surface, which is below freezing, especially when you have objects that are like metal and don't retain heat and cool very quickly, and easily can get ice forming on that. Sleet, similar to freezing rain as far as the process goes, it's just that warm air isn't as deep and it's not usually as warm. Then the cold air that's beneath the warm layer is deeper, so therefore anything that melts as it goes through the warm air is able to refreeze into those little ice pellets and winds up bouncing off the ground. In snow, usually you don't have any warm layer at all, and you can just continue to have snow and it be cold the entire column. There are some cases when we don't actually have a stereotypical or textbook examples like I just showed you. We can get freezing mist or drizzle when the surface is very, very, very cold. This actually occurred last year. This is one of our Facebook posts from last year. Unfortunately, I don't recall the date, but you start off with ice crystals and or supercooled water droplets, and then you have dry air that intrudes upon those ice crystals and supercooled water droplets. So therefore, there's not enough of them to form into snowflakes. So from that, you kind of just have mist hanging in the air in the form of those ice crystals or the supercooled water droplets. And when, say, your car is driving through that mist, it starts to ice up on your car. So it's not actually, in this case, it's not actually precipitation. It's mist that's hanging in the air that happens to be in air that's below freezing, and then when it makes contact with an object, like your car, as you drive through it, it starts to ice up. Now, I've used the term supercooled water droplets a few times, and like I said before, liquid water can exist at or below freezing. It's more likely to occur in air that's lacking what we call condensation nuclei. So what that is, condensation nuclei or freezing nuclei, depending on the temperature, is just dust particles and dirt and salt crystals that the water vapor in the air can glom onto and condense or freeze onto. Obviously, the higher in the atmosphere, the less dust particles and dirt and salt crystals that there are. So you have more particles near the surface. Therefore, the supercooled water, which is again just liquid water at or below freezing, is just more prevalent higher in the atmosphere. And when it's disturbed, like I said with the freezing mist, if you're driving a car through it, or in the case of the picture on the bottom right, the supercooled liquid water will turn to ice when it is disturbed, such as the turbulence formed by an airplane flying through. And I actually do have a video which I'm hoping will be able to show up for you guys easily. It's on YouTube, so I apologize. I have to skip the ad. So this is a bottle of water that has been in a freezer for an extended period of time, and it's still, because it is pure water, it is still liquid, even though the freezer has had this below freezing temperatures. And once it's disturbed, as they hit it, ice starts to form and actually turns the whole bottle into ice crystals. So I'm going to stop it there so that way we can continue. But it's a great example, and you can actually do that experiment at home. So going back to our mixed precipitation, what causes the layers of warm air and cold air? Generally speaking, we should all know that warm air wants to rise because it's less dense, and cold air wants to sink because it's more dense. In this case, when cold air sinks, it wants to stay near the surface, especially in protected valleys. So on the left-hand side, you can just see the general cooler air wants to sink and warm air wants to rise. Then below that on the left-hand side, it's just a simple depiction of valley between two protective mountain ranges, or even just a couple of mountains. And when you have a warm southerly wind moving across that terrain, the cold air in the valley is protected because the warm air is being blocked by the mountains. Another thing that can help cause these difference in temperatures is a warm front. As a warm front approaches and you have cold air, that warm air will ride up above the cold air because the cold air wants to stay down. It is denser, so the warm air does want to continue to progress, and it'll move up over the cold air, so then you'll wind up having warm air above cold air, which can lead to sleet and freezing rain if there's precipitation involved. Cold front, not as much, because the warm air gets pushed up as the cold air that wants to stay close to the ground kind of wedges its way or pushes its way into the warmer air. Another thing that makes our job a little difficult forecasting is the snow level will actually lower or get closer to the ground due to what's called diabatic cooling. And basically, when precipitation comes into an environment that's not completely saturated, in other words, the temperature and the dew point aren't close together, that precipitation will begin to evaporate if it's liquid water, or it'll sublimate, turning solid to a vapor if it's frozen. So a little thermodynamics for you. The thermal energy that is expended is going from the environment to the precipitation drop to change its phase. So in other words, the air around that whatever is falling, that snow or ice crystal, that snowflake, will absorb energy from the surrounding environment. That snowflake will absorb energy from the surrounding environment in order to evaporate or sublimate. This causes the temperature of the surrounding environment to actually decrease or lower, and at the same time, the dew point starts to rise. And you can see the red line on the right-hand side and the green line on the left-hand side do start to merge as the snowflake continues to fall and lower the temperature. So basically the red line, is temperature, the green line is dew point, and as the snowflake is changing phase, going from liquid to evaporating from liquid to a gas, or from a solid to a vapor or gas, they start to come together. Therefore, the temperature of the environment cools and the dew point rises, which causes the environment to become saturated, and eventually can lead to snow that was occurring, or will eventually lead from rain changing to snow in the same area. So basically, timing that can be very difficult, especially with the difficult terrain that we have here, and there may be cold pools, there may be warm layers, there may be drier areas. It's just another thing that makes our job a little more interesting. Moving on to how to measure winter precipitation. Overall, you want open ground that's protected by nearby trees, but not too close to the trees to cause any precipitation to not actually reach the ground in that area. You want to take several measurements and average them out, and using a snowboard, which is basically a white flat board, and a ruler. Just some tips for measuring snowfall and sleet. You want to measure snowfall and sleet as the same. They're treated the same, but ice is usually, when it's on branches and walkways and whatnot, you can measure that separately. So you want to try to measure every 6 hours before the snowfall melts, so that way there's no compaction or settling also. And you're measuring to the nearest tenth of an inch, and you want to try to get down as low as possible, so that way you aren't looking at it at an angle, and therefore you'll get the most accurate measurement possible. And don't forget, after you've taken a measurement, clear off your board for the next one. Now, measuring ice from freezing rain, best way to do it is take a branch and take your ruler and then do the measurement average. So if there's more ice on one side of that twig or branch than the other, you just measure the two and then average them. And again, measuring to the nearest tenth of an inch. So quickly going through our case study from about 2 years ago, you can see the tree completely weighted down by all the ice that fell as we had a warm front moving over the area. So this occurred December 21st through 22nd, and there were thunderstorms, sleet, and freezing rain reported with over 75,000 power outages, and $8 to $10 million in damage. And the airport here in Burlington actually used their entire year's supply of runway chemicals just during a 4-day period for this storm. The observed precipitation was 1 to 2 inches, and the ice accumulations were anywhere from a quarter of an inch to 1 1/4 inch. So here's a map of the storm total ice, and places that got hit really hard are in the kind of mustard color in the St. Lawrence Valley, and then we do have about an inch, 3/4 to an inch measured in the lower Lake Champlain, and a little bit of another peak in some of the higher terrain. But overall, many areas did see over a tenth of an inch of ice. And what caused that, you can see on this map, the freezing temperature, 32 degrees. Basically everything south of the red dashed line was above freezing, but then those areas hit hardest. The maximum temperature for the day on the 22nd remained below freezing, and therefore it allowed for lots of ice to form at the surface. Moving on to the next day, similar situation. Those areas that were below freezing for a high temperature on the 22nd remains below freezing for the most part on the 23rd, and then it even expanded down through the Champlain Valley all the way into Warren and Washington counties in New York. Here we have a thermal profile, and again, it's just the red line is the temperature, and the thick blue line in the middle, it's kind of a light blue, is the freezing temperature. So temperatures started below freezing, but then you had that very warm nose, that very deep and intense warm nose, with temperatures about 4 degrees Celsius above freezing. So that's plenty warm enough to allow for all that snow and ice crystals to wind up melting throughout that layer. And then about 1,000 feet above the surface, we started to see the temperature drop below freezing, and very, very cold, to -4 Celsius, or about 22, 23 degrees Fahrenheit at the surface. So again, you start off cold, then you have that deep, intense warm layer, and then a relatively shallow but very cold bottom layer near the surface. And then you can see how the temperature kind of progressed from 7 a.m. on the 20th through midnight on the 21st, and it just continued to have that very intense warm nose to the right of the 32 degree Fahrenheit line, while the surface still remained below freezing, and that cold layer right above the surface remained pretty shallow throughout the period. And I don't know why I'm suddenly stuck. Excuse the technical difficulties. Alright, I'll try restarting it. Apologize, but it's technology, right? So this is another way of looking at the temperature and dew point temperature. The red line is the temperature, the black dashed line is the dew point. The steady temperature lines are actually slanted or skewed. We call it a skewed T. So, but you can see the thick blue line is the 0 degrees Celsius or freezing line, and the temperature and dew point going from the surface, again, a very, very shallow layer, and this was taken from Buffalo as one of their upper air soundings. And as you go higher in the atmosphere, you have that warm layer from about 925 millibars to 700 millibars. So, in other words, just a very deep layer of very warm air where the temperature actually went above freezing by about 10 degrees Celsius, and then around 700 millibars went back below freezing. Important things to note here is that the wind barbs on the right have a very strong southwesterly flow, which is helping to bring in some of that strong warm air, as you can see in the area highlighted in red. But at the surface, there's actually some cold air being brought in by that northeast wind, and that's down at the bottom. So that's what gave us the setting for all that freezing rain. Looking at the surface analysis on December 22nd in the morning, 8 a.m. or 12 Universal Time, we have that warm front that's actually stretching across New York, Vermont, New Hampshire, and into coastal Maine, as well as the shaded areas being moisture that is going to be moving up with that front. Some ice storm photos. Lots of trees down, lots of damage. Even for days afterwards, the trees' branches continued to break just from all the ice loading. So in summary, we had cold high pressure to our northwest, which resulted in continuous advection or filtering in of shallow cold air into the valleys. Then we had that front that provided lift for precipitation, and the ice accumulation was highly terrain influenced. Basically above 1,500 feet, it was warm enough where there were not a lot of reports of ice accumulating, and below that 1,500 feet in the valleys, that's where the shallow cold air was, and that's where around an inch was received in the St. Lawrence, Champlain, and Missisquoi valleys. So, last couple of slides. Now that you know a little something about mixed precipitation, you can go to this website, which is scijinx.jpl for Jet Propulsion Lab, .nasa.gov/precipitation-type, and you can actually fiddle around with the temperature and dew point to make the precipitation change. So you can have it be all snow, change the temperature towards the surface, and make it freezing rain or sleet, and just see exactly where that point is where you can go from sleet to freezing rain, or vice versa. With that, we'll take some questions. So again, in the chat dialog box, please type in your questions, and I will answer as many as I can in about the next 5 minutes. So, let's see. That up. Here we go. Okay, early in the talk, someone asked to define the geographic bounds for the North Country. We refer to the North Country as our county warning area, which extends to the St. Lawrence Valley in New York to the west, across Clinton and Franklin and Essex counties, across the Champlain Valley, and then into Vermont. We have all of the Vermont counties except for the southern two counties of Bennington and Windham, which are under the Albany, New York office's county warning area. Another question, so sleet always manifests itself as little balls once it hits the ground. Yes, technically sleet is defined as a little ice ball. It could be partially melted, so it may kind of splat a little bit. It may be an ice ball, a small ice ball surrounded by water that's still adhering to it. So it may not be, depending on how cold it is and how deep that layer is, it may not be a perfect ice ball. It may be an ice ball within surrounding water. Let's see. One person asked, how do you collect temperature readings at all the different altitudes? Not particularly at our office, but at approximately 92 offices within the Weather Service, we release a weather balloon, which literally is a balloon with an instrumentation package attached to it. We release them at least twice a day around the country, all at the same time, and they take readings of temperature, dew point, wind, and pressure as it moves up in the atmosphere. We also can, using different surface weather stations at different altitudes, build a similar profile of what the temperature and dew point are. There's a few questions regarding El Nino and mixed precipitation. Unfortunately, there's not necessarily a clear-cut answer to that. We are in a strong El Nino, as I'm sure you've heard, in which case we actually have a newsletter coming out soon with an article on that describing what El Nino is and how strong it is and the impacts. Because El Nino occurs in the Pacific, it has a much more direct impact on weather in the western U.S. as well as across the southern United States. They typically get more precipitation events or higher amounts. Because we are almost butt up against the Atlantic and much further removed from the Pacific, there isn't as a clear-cut, direct relationship. So we've had years where it's been a strong El Nino and it's been dry and warm, and we've had years where it's also been a strong El Nino, but it's been wet and cold or wet and warm. So we, unfortunately, like I said, there's no clear-cut answer to that. So someone asked about the rain-snow line seen on model data, for example, the GFS. Rain-snow line is literally just the freezing line where at the surface the model is forecasting or depicting the separation of rain to one side and snow to the other side. And that's just based on temperatures. Sorry, my dialog box, every time there's a new question, moves, so it's hard to keep track. Sticking with the weather models, where can you find weather models like the GFS and the ECMWF, which is the European? You can find them actually just by Googling. Actually, I'm gonna ask my, coworker here. NCEP, they have a whole bunch of suites, model suites, and I, off the top of my head, do not know the website for that.
Yeah, it's kind of a complicated web link, but they do have several. They do have several kind of model guidance output that's available. It's on the website. Actually, if you just type into Google, NCEP models, you'll find a link that will direct you to where you could find those models publicly available online.
And the NCEP is NCEP, National Center for Environmental Prediction. So there's a question here regarding what I said about snow. Why is 540 millibars the magic number? A very quick and crude way for us to get a idea of what the models are predicting is to look at the thickness heights for 500 from 1,000 millibars being close to the surface to 500 millibars. The 540 line is actually it's not millibars, it is actually decameters. So when you look at a weather chart and you look at 1,000 millibar chart, it will actually, the lines on that chart will be what the height of the 1,000 millibar pressure is. And the same thing goes for at 500 millibars. So 540 just depicts that usually on the northern side of 540 means that it's colder air throughout 1,000 millibars, which is close to the surface, to 500 millibars, which is about midway. Like I said, it's crude, but it does give us an idea of what the temperature is based on how high, because if you have colder air, the air is going to be more compressed because it's denser, and that'll signify cold air for us, just to give us a heads up of, hey, you need to look at this area because the 540 line is there, and that means there could be mixing as it transitions from warmer air to colder air, or it could be just that that's when the snow is going to be, or the precipitation is going to be in the form of snow. So, and I'll take one last question. What is hail then? Because we didn't go into hail because this specifically mentioned winter precipitation, mixed precipitation. Hail occurs from actually thunderstorms that have an updraft. So hail starts off as usually water or ice in a cloud. That updraft brings that particle high enough where it's freezing, below freezing. So if it was water, it winds up freezing into a little ice particle, and then basically throughout the life cycle of that hail particle, it winds up falling because it gets out of the updraft and then goes back into the updraft. As it falls, it may actually go below freezing again, melt a little bit, and hit other particles of water droplets or ice particles. As it goes, the updraft catches it and brings it back up above the freezing line, so it freezes. So it's just like cycling and therefore building due to the fact that it's crashing into all the other particles in that cloud. Eventually the hailstone grows and becomes heavy enough where the updraft can't carry it and it falls out of the cloud. So with that, I know there are many other questions. I can try to email everyone. If you provided an email, I can try to answer them in the next coming weeks, but I may not get to it until the holidays. So unfortunately, my time is up. Thank you very much for attending, and if you have any further questions, you can always email us at excuse me. On our website, we do have an email address towards the bottom. I believe it's the BTV or Burlington Webmaster. So thank you very much for your time, and happy holidays, everyone.